Well, good afternoon, and welcome again to day 3 of the 2021 Humans to Mars Summit. My name is Chris Nelson, and I am the Strategic Planning and Architecture Lead for the EVA office at Johnson Space Center. My role within the EVA office encompasses responsibility for establishing the strategic plan and managing the portfolio of targeted technology development, along with fostering partnerships and collaboration across the agency, with industry and academia, in the pursuit of the most effective future EVA system to meet our collective mission objectives. I'm really excited to be here, and I'm grateful for the opportunity to moderate this outstanding panel on EVA Suits and Operations. Since the Gemini program, and specifically June 3rd, 1965, EVA, or extravehicular activity, has been a part of every NASA human spaceflight program and has embodied the human passion for exploration. Images and video of EVA crew members, alone, surrounded by inhabitable conditions, and separated from nearly everything else, are an iconic symbol of the essence of human exploration as they press beyond boundaries of the seemingly impossible in search for knowledge and truth. Throughout the history of EVA, we have sought to build and test the best spacesuits and tools to match the job required for the mission at hand. Beginning with those first U.S. EVA spacesuits known as the G4Cs. They were simple suits weighing no more than 34 pounds and designed with a focus on supporting life in the vacuum of space. The Apollo program required suits enabling crew to walk on the moon and carry their own life support system while facilitating bending and tool usage on a planetary surface. The shuttle program employed suits to enable retrieval of old satellites, repair of sensitive science platforms like the Hubble Space Telescope, and construction of massive orbiting outposts like the International Space Station, where these same suits are utilized today to enable maintenance, contingency repair of failed systems, as well as the upgrade of science platforms and vehicle systems aboard our home in space. With each successive mission came a demand for new suit capability to enable human performance in extreme environments not previously envisioned. What will future missions demand of human explorers? And what suit capabilities will we need to develop to enable that exploration? My hope is that we'll help shed some light on that through this panel discussion. But before I introduce our panelists, a quick logistical note. Our desire is that this panel will be as conversational as possible, and that includes you. So throughout the panel this afternoon, please post your questions for our panelists in the chat, and I'll work to integrate those into the discussion. Now, without further ado, I'm joined today by Natalie Mary, who is experienced in human spaceflight as an accomplished flight controller for the International Space Station program, and now serves as a lead systems engineer in the Exploration, Integration, and Science Directorate's EVA office at Johnson Space Center. She currently works for the Aerospace Corporation, providing support to NASA's EVA community with a focus on systems engineering and integration of requirements, architectures, interfaces, and operational concepts for multiple missions, including the ISS and exploration spacesuit capabilities for cislunar, lunar, and Mars missions. Along with Natalie, we have Dr. Ryan Kobrick, who is a principal investigator and aerospace engineer with Paragon Space Development Corporation. Ryan formerly served as an assistant professor of spaceflight operations in the College of Aviation at my alma mater, Embry-Riddle Aeronautical University in Daytona Beach, as well as principal investigator of the Embry-Riddle Suit Lab, which stands for Spacesuit Utilization of Innovation Technology Laboratory. He has served as a crew member of 6 simulated Mars missions, which included a 100 operational day simulation on Devon Island. And Dr. Kobrick's research focused on reach and work envelopes using motion capture, analog research, lunar dust abrasion, global engagement, and lunar Martian surface operations. Rounding out our panel this afternoon is Dr. Gregory Quinn. Dr. Quinn is a principal research engineer and the chief engineer for advanced spacesuit technologies at Collins Aerospace. Greg's current work is focused on advanced spacesuit design with an emphasis on the portable life support system. His responsibilities include directing all spacesuit-related R&D and serving as the subject matter expert on advanced spacesuit contracts. Like Dr. Kobrick, Dr. Quinn is no stranger to analog testing and has participated in field research on Devon Island for the Houghton Mars project in 2005, as well as contributing to the NIAC chameleon suit study in 2003. He has over 20 peer-reviewed papers, 5 patents, and serves as a session chair for the International Conference on Environmental Systems, serving continuously since 2012. A big thank you to our panelists for being here with us and participating in this panel. To start this afternoon, let's hear a lead in to our topic from Dr. Ryan Kobrick, who has captured a recording for us, and we're glad to have him here to join us for questions and answers later in the panel.
Yeah, I'm happy to be here, and let's watch the video. I don't think I could do it better than that anyway. So we've got...
Hi there, I'm Ryan Kobrick with Paragon Space Development Corporation. And if you're watching this video, it means that I'm somewhere in Florida helping support and watch my good friend Cyan Proctor launch to space with Inspiration 4. It's a pleasure to be part of this summit, and I hope to be there next year. And please feel free to send me questions as they come up on social media or through email. I've provided all that at the end of the short kind of presentation introduction that I've got for you today. I've always been fascinated by spacesuits. I love them. I think they're the coolest thing on and off the planet. Everything you need to survive in space is right there. This is the world's teeniest spaceship. You've got life support, you've got equipment to communicate, everything you need to survive, at least for a certain duration. So I've always been fascinated with how we're able to create this cool thing and how we're going to make many more in the future. The Spacesuit 101, just in case, we've got a very diverse audience, and I want to make sure that everyone has a basic understanding of what a spacesuit does and its functions. Essentially, there are 3 tiers for life support systems. Number 1, you absolutely have to keep the people alive. So worst case scenario, you could throw them in a bubble with some oxygen and some CO2 scrubbing, and you'd be able to get them down safely. The second is to actually be able to do their job and function. So the second tier basically meaning that, when we think about zero-G EVAs and spacesuits, you actually have to have hands and ability to see and visual aid and communications so that you can complete your job. And then number 3 is comfort. We want to prevent injuries. We want to make exploration as easy as, it feels like you're not even wearing a suit. That's a huge stretch goal in design, but for the most part, that's where we're trying to go. And if we're going to be living off the planet and onto Mars, we need to be able to comfortable in our work clothes. So the rule of threes, really people should know about this, is that without pressure, you would last 3 seconds. Without air, 3 minutes, meaning a lack of oxygen. Without shelter in an extreme environment, 3 hours. Without water, 3 days. And without food, 3 weeks. And so if we look at the human body and the inputs and outputs, these are really the consumables that we need to think about when we're designing any system. We've got oxygen, portable water, and food, our energy sources kind of coming in. And then the things that we generate as humans, waste, trace contaminants, CO2 is the big one there, are really the things that we need to consider while we're designing. And, just as we think about other consumables, we also have to think about the price tag on a lot of these things. It's more of a throughput than a consumable, but it is important in terms of spacesuit design. This is not a super simple thing to do. So there's a lot of cost of development to make these things efficient, robust, and safe. And if we look at the subsystems, this of course looks more like a habitat than a spacesuit, but it really gives you a breakdown of all the different major life support systems, everything from the atmospheric revitalization system all the way to thermal control, all areas that Paragon has specialties in. Each of these subsystems then has assemblies, and each of these assemblies are then combining different technologies. And for the most part, Paragon has experience with all of these different technologies over the last 28 years of doing life support and thermal solutions in extreme environments. So a few Paragon highlights, just to let people know a little bit about us. We were part of the Constellation Spacesuit team led by Oceaneering. We were leading the thermal modeling and analysis. We even designed and delivered thermal control and PLIS hardware. That's portable life support system. That's the backpack with all the hardware on the back of the astronaut. We had a full from design to flight program, spacesuit program. The StratX mission was the first operational spacesuit built in the US in the last 30 years at the time that it was flown. And this broke altitude records and won awards, of course, and is now, if you want to go see it, you can go see it in the Smithsonian in Dulles. The Paragon dive system, again, looking at extreme environments here, just to give an example, with this hazmat suit to deal with contaminated water. Finally, just to kind of highlight on some of our major programs. I mentioned StratX. I mean, it's an all-in-one suit, and my little camera thing's blocking the words there. But we were also part of the human landing system, working with Dynetics on doing the life support and internal thermal modeling for that program. And that all came out of our commercial crew transportation air revitalization system, the CCTARS. Leading to the maturity of these next designs, and now currently on the HALO program as the provider of life support with Northrop Grumman, preparing Gateway for going around the moon. So what's going on in spacesuits with, I guess you could say USA Today, because this is a USA slide coming up specifically, is the EMU, which has been the upgrade to the current ISS design, and that's in its progress, and we'll talk a little bit about that in the coming slides. You can see SpaceX's IVA suit here. David Clark has 2 suits here for both Boeing and for the Orion program, and these are kind of the next generation get me down launch entry abort suits. So IVA, for those that don't know, is the intravehicular activity suit, so that's inside, and EVA being extravehicular, meaning outside of the spacecraft, the main spacecraft. So what is the XEVAS opportunity? That's just coming out now. The RFI indicated that there might be 22 EVA suits under this contract. That would also include services. So is that servicing the suit, the tools, the training? And so the draft was out in July. And right now there's a draft RFP out for this call with the release date coming up next week. And 30 days later, the proposals will be due. And that is for $3.1 billion being invested in spacesuits over 10 years, and multiple awards are possible. So that contract wouldn't start to March. And really, this is a huge opportunity. This is like the decadal call for spacesuit technology development, and the part of the Artemis generation suits. So just kind of finalize in summary here, like where we are is that this program that's coming up for XEVAS is really focused on ISS replacement development for low Earth orbit, looking at Artemis for the moon and our moonwalkers, and then the advanced version of the suit, which is for Mars, essentially. So it's really Mars forward thinking. As you would think through the design process, you want to be able to have a suit that's modular, robust, and able to configure to these next upgradable programs. If you've got any questions, feel free to reach out to me. I'd love to obviously be there right now with everyone and be part of the ongoing chat. Maybe I'll be there for the Q&A, I'm not sure, but feel free to reach out to me. I look forward to all of our futures in space. And this is the challenge for all of you to spacesuit up, and I'll see you out there. Thanks. Bye.
Yeah, thank you for that, Ryan. And what a great introduction to talk about spacesuits and what they do, and even for current U.S. spacesuit activities. And to your last set of slides there, the investment that's being made in suit technology for taking us further beyond where we are today. We're so grateful for you being here with us, much to the end of that. And so look forward to the discussion a little bit later. With that, though, I want to kind of turn it over to Natalie to give us a little bit more details on the XEMU and what that looks like for current suits and future suits alike. So, Natalie?
Great. Yeah, happy to be here. That was a great introduction, Ryan. And so we do have, I thank you for the Suit Up reference as well. We do have a public-facing website that's right there, nasa.gov Suit Up or /Suit Up. And so that's a good place to go see any public information that we have. We have ConOps that were concept of operations for both the moon and Mars out there, and different concepts that we've looked at for alternate ingress egress methods, different kinds of airlocks and suit ports. And there's a lot of good videos and pictures on that website for you to take a look at. And so next slide. And so again, great introduction, Ryan. Currently, we're working on the Exploration EVA Mobility Unit, the XEMU. And we do like to think of it as a personal spacecraft. And so in that, you have to have your comm, your informatics, your removal, oxygen, mobility is key and fit for crew comfort, and dexterity to be able to perform tasks on the lunar surface. Well, cislunar gateway, ISS, and the lunar surface and Mars, and even transit to Mars. And so we incorporate that enhanced upper mobility by moving in the side bearings and having more shoulder and arm mobility, as well as the extra bearings in the legs that allow you to walk in a planetary environment. And then protection with the environmental protection garment all over the suit for thermal, micrometeoroid, and dust. And so several things we are doing right now is actually testing a lot of those technologies through our DVT testing, design verification testing, as we are looking at bringing the EVAS contract on. And we are also incorporating a lot of things that are forward for lunar surface sustained missions as well as Mars. Some of those things are going to be enhanced informatics, enhanced environmental protection garment, the actual set points. Usually for ISS, we're at about a 4.3 PSID in the suit. For enhanced or shortened pre-breathe technology and protocols, we're looking at having a range of set points from 4.3 to 8.2 PSID. And that will allow, if the vehicle's at that atmosphere and the crew members at that atmosphere, if there's a new technology or concept that comes along like a suit port, we would be able to egress the vehicle a lot more quickly with a reduced pre-breathe duration and actually still have that mobility at that higher set point for 8.2 PSID. And then we do have a CO2 removal system. It is really more of a vacuum, but operates in vacuum, but it's regenerative opposed to previous technologies like LIO and MEDOX. And so we're really happy with that. But for Mars, we'll need to look into that technology or alternate technologies more with a CO2 atmosphere. And then also, thermal cooling. And then we've got the current design has the rear entry, ingress, and egress, which could also be compatible with something like a suit port. It also allows easier ingress into the suit with less injury for the crew member. And so we're looking at using that on the lunar surface or a similar version of it from a contractor, and testing out certain technologies, understanding more about reliability and what we need to do to get to that Mars suit. And so with that, the next slide, we have significant challenges for a Martian suit. An EVA suit for Mars is going to have a different environment, different partial gravity. So we're looking at thermal and CO2 removal technologies and capabilities for a Mars suit. A lot of other differences will come into play with crew autonomy, with the long comm dropouts and latency for communications. We'll want to have the ability for the crew to be able to perform tasks on the Martian surface and make decisions without mission control center being right there, and how we're operating today on the ISS. And then planetary protection is also very interesting, both backward contamination, as in once you're leaving the Martian surface, you want to be able to break that chain and leave as much Martian dust and environment behind as possible, so that you're not bringing things back to Earth. And then forward contamination, where we don't want to bring biologicals from the human and introduce them to Mars and then discover life on Mars when it's really just something that has been leaking from the suit, or which the suits are designed to leak to a certain extent. So all sorts of protocols, and it'll take an integrated approach with planetary protection, but it is something that we're looking at for Mars as well. That'll also play into your operations, where you go on the Martian surface, and things like that. And so the thermal environment is also going to be very different. It's more of a convective thermal environment. So that's another thing that we've looked at in the past during the Constellation era, and need to bring that forward again and discuss that. And with the partial gravity, the mass challenge is a very large challenge. No pun intended. But you've got a very heavy spacesuit right now, which actually helps in the lunar gravity with walking and mobility. But for Mars, with 3/8 gravity, is going to be quite the challenge. You don't want that much on back mass when you're walking around on an EVA and performing science tasks. So you need that mobility. You need to be able to have all of the life support functions that we need in your personal spacecraft, your spacesuit, and be able to perform those tasks. So there are a lot of different options that we're considering and looking at for that mass reduction aspect of things. And so I think that's the end of my charts.
Yeah, I appreciate that, Natalie. And a great overview of kind of the current exploration EMU system and kind of the government reference design, I think, is how it's generally referred to. And even, hitting on some of the challenges that we're going to spend a little bit of time talking more about in the questions and answer and discussion section. But kind of leading into that, Greg, I'm going to turn it over to you to kind of do a quick intro, but then also talk maybe about some of those enhancements as well.
Sure. Thank you. So good afternoon or morning or evening, depending on where you're joining us from. I'm going to talk, I've just got 2 slides, a little introduction of my background and where my passion for space comes from. I'm sure many of you have similar stories to tell. And then I'll talk a little bit about the challenges that I see as from a technology point of view in designing the next spacesuits. Next slide, please. So many of us have been driven towards an interest in space. I can say from my experience, the first part was a children's book. I read a book about a boy who went to a space station. And you can imagine my disappointment, 1, that boys couldn't go up into space, like 8-year-olds. And 2, that there wasn't a space station at the time. So I was really disappointed. And I sort of got the spark to do something about that. By high school, I knew I wanted to help put someone on Mars. And that was reinforced when I saw the thrilling success of Pathfinder land and move on the Martian surface. It was amazing to see and to know that we could do that and put something that moved on Mars. I also see putting people on Mars and getting there as a pinnacle of engineering challenges. I'm an engineer. I love those challenges. The technology is fascinating to me. And I love solving the problems that need to be solved that haven't been yet to move us forward as a species. So I've taken a technology-focused path in my career. I've been at Collins Aerospace since 2000, where I started my career. I've had the privilege of working on spacesuits almost that entire time and various life support systems. So, scrubbing carbon dioxide out of the air, conditioning humidity, temperature, providing pressure to the crew member. I've also worked systems engineering development on the larger architectures to help everything snap into place. So if we design a pump or a fan or a heat exchanger, that it works in a larger system. A couple of the highlights was mentioned before that I've worked on the chameleon suit study. That was a 30-year look forward into what a spacesuit could be, where you take all the functions that are in the backpack now, and could we distribute those within the suit itself, use the environment, use the suit and emerging technologies to make the spacesuit seamless to the wearer so that you get the the functionality and the comfort beyond keeping the person alive. And as was mentioned before, the picture on the right is I'm photobombing the mock-up spacesuit there on Devon Island for the Houghton Mars project, where we were testing out informatics, how to provide the crew member with a data-rich environment and additional situational awareness that is far beyond what the crew members have today. They have their audio, they have a little one-line LCD display that tells them the status of their suit, and a paper cuff checklist. So not very high technology there anymore. And we know that it's mission enabling to provide those additional features that we all expect. We all have our cell phones and can call up Siri or Google or anything we want at a moment's notice. We want to be able to provide that to our crew members as well. Next slide, please. So what are some of the engineering challenges as we try to enhance the spacesuit to get the XEMU on the moon and then on to Mars? First among them is designing a safer spacesuit. We have had a fantastic safety record on the EMU. We've had hundreds of EVAs, and during EVA, no injury to the crew members. But we're going to have even more frequent EVAs, which means that the incidence of failure has to be as low as we can feasibly make them for those crew members that will be wearing them. We also have to enable greater ConOps. Right now, we have stringent rules on when and how to perform EVAs on the space station. When we go to the moon and then on to Mars, we have to provide an ability to operate the system with more flexibility than we have today to accommodate contingencies that really need immediate response from the crew members and can't be choreographed around. Finally, and it was mentioned already by Natalie, that we have to allow the users autonomy, less control from the ground. They're going to have COM latency, extreme COM latency on Mars, and they're going to need to be able to have the system make decisions for them, for itself, and provide them with actionable information in a way that is not available on the EMU today. We do need to provide the crew with enhanced capabilities in addition to safety. So less maintenance and preparation time for EVA and more time out the door. You don't want to be always working on your car. You want to be driving it, right? The crew love to go EVA, and they'll be going on EVA a lot more, and we need to let them be more productive with their time. They'll need a rich data stream. The amount of time between training and actually executing the missions could be months, and on Mars, years. So I know I don't stay trained on how to swap the brakes on my car. I pull it up on YouTube and I have the video in front of me. We can provide that type of information to the crew members now in a new system. It also has to be part of a seamless part of the exploration ecosystem. So there's going to be that rich data stream, but also tools, robots, vehicles, the landers. We have an opportunity to look ahead at all those assets and make sure that the suit is working with all of them, interacting with all of them in as productive a means as possible. So with the vehicles and platforms, we have line of sight to the space station, needing it to work there, the human landing system, gateway, lunar terrain vehicles, and future commercial platforms. So that's a lot of requirements, a lot of people that will want to use the next versions of the suit. And designing around all of that is going to be an engineering challenge, but the community has been working at this for quite some time and has a lot in their pockets ready to go to provide these capabilities. And that's it for my introduction. Thank you, Chris.
Yeah, absolutely. Thank you, Greg. And again, I think thank you to all three of you, really. I think it is just a great introduction across the board, kind of from a spacesuit 101 into kind of the current, development that's been going on within the government side of the house, and then looking down the road to what are those advancements and those enhancements that we need. And so those are the things that I want to pull on. But I want to kind of maybe go back, and Ryan, I want to ask you maybe the first question, and this is going to be a softball, right? So just go with it. But, in your introduction, you kind of gave, you mentioned three or a number of U.S. suits that are in works, that are in the works these days. And three of those were IVA, and one of those were EVA. And again, we're here to talk about EVA suits in particular. But I hear it often. Many people these days talk about the slick design of suits like the ones you showed from SpaceX and David Clark. But there are some fundamental differences between an IVA suit and an EVA suit. And just for the sake of rounding out our audience, can you give some insight to the differences between these two categories of suits, IVA versus EVA, and the capabilities required for each?
Yeah, absolutely. Yeah, the big difference is you're walking out the door. You're not, safe and protected by that shell of a spacecraft. And so without that spacecraft, that means that you need to deal with a micrometeorite possible environment, like if we're assuming 0G here. You have to deal with radiation protection, and you have to deal with the harsh thermal environment. So all of those are kind of added on. And then we think about going from a 0G suit then to a planetary suit. There's also a huge upgrade that has to happen as well. Now we've got to walk. We don't even need legs on a spacesuit for 0G. I joke that you could be, in a sleeping bag shape, have not even legs, like as long as it attaches to, your foot restraint. It could be the sleeping bag restraint. It doesn't matter because it's all up here. It's all upper body work in 0G. So once we go planetary, Moon, Mars, we need to be able to walk and function. We need to be able to bend, do samples, and all the scientific data collection that's necessary with not just geological, but biological field work. So those really become the next level of systems that have to be into the design. My background is also in lunar dust abrasion. So especially for the moon, we need dust tolerant systems. It doesn't mean just mitigate the dust, but they have to be able to survive and last for, a certain number of EVAs, whatever the contract may be on that suit. And so all those things need to be factored in as you go up the scale of difficulty of different types of suit. So literally it could be, bubble person at the far one extreme of like very basic, like keep the pressure and get them to safety, which is really what when you think about like the medical industry and some of the like emergency chambers that need to be used, that, goes from the very basic to the extremely advanced of actually helping someone breathe, which would be, the super advanced, spacesuit that helps keep you alive with medical provisions and other things.
Yeah, no, thank you for that. And I think you hit on a lot of the key elements there, right? So when you get out the door and you start entering the dangers of space, as we talk about lunar, obviously, and we talk about Mars, there's vacuum, there's partial atmosphere. You mentioned thermal, the extreme hot, the extreme cold, micrometeorites was one that you mentioned. Radiation's another one. Natalie, as we think about maybe the operations that we're thinking right now for lunar surface EVAs, are there particular operations that maybe compound those challenges? Ryan hit on dust, but anything you want to add to that list?
Yeah, dust is a huge one, which we're working on dust mitigation tools and things like that before you get in to the vehicle or the habitat or the lander system, as well as what you do when you're inside. But along the lines of lunar operations, and we're going to learn a lot from the lunar surface on that, there are some differences that we'll really need to take into consideration between lunar and Mars. But beyond the dust, other environments, there's going to be the thermal aspect is going to be so much different on the Martian surface than the lunar surface. And we're also talking about operations-wise going into even more extreme areas of the moon, like permanently shadowed regions or something that's been in the dark for so long that we really have to take into consideration. Well, are we going to need glove heaters? Are we going to need, how long can the astronaut and the materials be in that kind of extreme environment? And so probably, going to limit some time on being in those regions. And then the lighting is going to be very different. Being able to navigate in different extreme lighting scenarios, being able to have the communications on the lunar surface and navigation in those areas, and the informatics to help you navigate all of that. So there are a lot of differences there. And then trying to think of some similar operations might be some of the vehicles that we'll have for Mars. If we're looking at going towards a pressurized rover and we're looking at suitport technology, then that's going to really, if we test that out on the moon, that's going to really be a step forward to helping us understand what we can do on the Martian surface as far as ingress, egress of the vehicle, dust mitigation, suit maintenance. How are we going to maintain the suit? You're going to have to, even on ISS right now where there's no dust, we've got to change out the gloves pretty frequently, every 3 EVAs or 4. And so that's something that we'll need to understand. How are we going to do that? What are the logistics like on the moon versus Mars? What are we going to do as far as the quiescent period? If you're sending a lot of pre-deployed logistics to the moon for a certain amount of time versus Mars for a much longer period of time, and what is the lifetime of those suits, and how do we understand that cycle life and manned pressurized time life of the suit? And so there's quite a bit of differences there, but understanding how that works on the moon is going to help us understand what we need to do for Mars.
Yeah, I think that's all great information, right? And there's a couple of parts to that where it highlights the integrated nature of this, right? So we're talking about a suit, but there's also a habitable element, right, that plays out. And so how do you integrate that and consider that? You hit on lunar dust mitigation, things of that nature. Certainly you brought up suit port as to what Dr. Quinn was hitting on with more frequent EVAs and maybe more time out on the surface, also helping with some of that dust mitigation. And you even hit on the life of the suit. So there are actually 2 questions that fit into that. One is the lunar surface, the dust that's there is generally considered to be glassy and abrasive and will have a big effect on the wear and tear of the soft goods of the suit. The Martian dust, though, is generally considered more fine and clay-like with maybe some corrosive elements. Is there an overlap in the materials development? Maybe Greg, you want to try and address that? And how would that potentially affect the lifetime of suits?
Sure. So the Martian dust, the means that are being developed now to mitigate dust, the first protection against dust is the environmental protection garment that covers everything, because it's got to protect from cuts, from micrometeoroids, from incident radiation, from the sun, for thermal purposes. That layer is also going to be used to keep dust from getting further down into the system. So that's the first layer of protection, and I would expect, and from what I've seen in the development, that first protection would be effective with both glassy dust and the fine dust from Mars. It's not going to be perfect in either case, and it will get down further, and it'll also pick up dust to come back to the habitat if it's brought inside. So other means are for like the joints, the mobility joints, the bearings. We learned from Apollo that they started increasing in torque significantly within 3 EVAs. So there are certain means that are being used to repel the dust from those bearings to keep them out of the rolling element parts of them. As far as removing dust goes, to keep it from accumulating, the brushes don't really work with the glassy material. There are ways of using electric fields if it's polarized to repel the dust, vacuum it up, air, use air to blow it off. Some of these means are going to be tested. The final tests are the early lunar landings. We have a lot of resources to test dust, putting items in tumblers. We have lunar simulants, we have Martian simulants, but ultimately we'll know from those early lunar landings what we got right and what we didn't. And we'll need to go back and continuing engineering and upgrading the system to accommodate the needed changes.
Yeah, that's a great point. We often talk about in-suit design, right? The design process and the test process, and then the redesign process, right? And just the inherent feedback we get from analog testing scenarios and humans in the system itself. And I appreciate you guys kind of hitting on those. It actually addressed a couple of the questions from Chauncey Wilson.
I had some add-on for that as well.
Go ahead, Ryan.
Yeah, so with all the analog testing, I think that a big part of the design is also the operations and how the user is going to use the suit. So when I think of dust busting, if you will, like dust mitigation, I really think of it as in 3 major stages. Everything's in 3, right? We're talking about like life support here, but the first is really the operations side. How do we operate to minimize falling over, taking a proper sample, bending, all those techniques that the astronauts are currently learning with offloading devices. Going through that, dress rehearsal, if you will, is what'll first help reducing the dust. Then it gets into the systems that Greg was just hitting on that are actually going to mitigate them on the suit, preventing it from penetrating the suit or getting in bearings. Abrading the visor, the astronauts had trouble seeing during the Apollo missions. They had trouble seeing their gauges because they were getting scratched. So all those things then become now we need the materials in the right design. And then the third kind of level is, well, dust is going to get into the habitat. We can expect they're going to get dirty. They're doing science. They're doing field work. So it's then the systems of the lunar lander that's going to have to take care of it. And the work we were doing previously on Paragon was looking at HEPA filters and the effect of dust simulants, at least, on those filters and how we design to deal with the expected load that might be coming in on each EVA. It may not seem like a lot, but it was like 100 grams per EVA for like 2 suited crew members. And it adds up, but it's also going through a lot of other environmental factors in terms of, there's pressure change, there's electrostatic charging, adhesion to surfaces. And so it's not just the suit. The suit is kind of like the front lines of preventing the dust from actually getting in the first place.
Yeah, no, those are great words and highlight back again to that integrated nature, right? So the suits play a role, and as you hit on, are the first line of defense maybe in this, and the dust adhesion and repel part of that. So maybe I want to ask a question, Natalie. I guess maybe I'll ask this to you, and then we'll kind of see if Ryan and Greg have some additions they want to add to it. But Ryan captured kind of these 3 items that he termed the fundamental tiers of life support design. And that included kind of in that order, keep the human alive, right, as number 1, be able to function as number 2, and then comfort as number 3. And so I'm assuming you generally agree with those. And I suppose the question that I have centers on the concept that the more capability that you drive into a system and add, the more complex it becomes. I guess first, do you agree with that concept? And if so, can you speak maybe some to the complexity that's encountered as the EVA community has added more capability to the suit system?
Sure. Yeah, we actually, one of the things that we have added in, based on lessons learned, but also working with ISS, is that fault tolerance aspect. And understanding what all we need in the suit for oxygen and thermal removal and CO2 removal. Thermal insulation and thermal ventilation and cooling. And so we do have added capability in the suit, which does add the mass and complexity, but it also will allow the crew member to be able to perform, say, an hour walk back approximately, depending on their met rate, terrain, lighting, navigation, all of that, your communications. And so that is something we've also incorporated lessons learned from ISS and separating the vent loop from the cooling loop. So there's a lot of different things that we have added. Once you start adding in more informatics and being able to have those displays in your helmet, that can also add to the complexity and software of the suit, but something that we may need, for more autonomous operations going into the future. Suit port capability is also it will definitely add mass and complexity in the EVA system, but could be something that will help the operations and decrease the amount of time that it takes for a crew member to egress an airlock. So instead of full depress of an airlock, you're looking at that small vestibule to depress, adding in the mobility for that capability at a suit that's at 8.2 PSID also adds that mass and complexity. But again, you're getting out the door a lot quicker. And so, yeah, there's quite a few things when you add in, and there's definitely an argument to say that you make it, more simple, that works, then you probably would have less failures and things like that. There's going to be a need to be able to maintain those more complex systems, especially when you're going for longer and farther out to Mars.
Yeah. So, Greg, maybe it'd be good for you to kind of press into that tension, right, that exists there. You kind of highlighted in your introduction, some of the additional enhancements. With that, of course, we have the other side of the coin of mass constraints, right, and really trying to drive a reduction in mass in order to enable some of the mobility there. Can you speak to that tension and maybe the optimization problem that plays out there?
Sure. It's the added capabilities have to be there. The users need those capabilities to perform their mission. So the question then becomes, and the challenge, and it's not an easy challenge, is how to manage that complexity. For the informatics, for example, there's the idea of automating a lot of the functions of the suit so that the users don't need to have their cognitive overhead engaged in those operations, and that the computer can do them faster than the operator, again, to get them out the door faster. So that's where we can take some of the complexity that's necessary for the capability and bring that cognitive load off of the user. It's in software and it's in electronics, but it's manageable. And that's one way to sort of to manage the complexity of that. Some of the other complexities, it ends up being a systems issue. If you can open up that box to help continuing to solve those problems that have a solution today, but will want to be lighter weight in the future without giving up those capabilities, you have to open up the box and start solving it as an entire system. There are papers and ideas of offloading the life support onto a FIDO rover that follows you. That's where you're using additional assets and not just the suit to perform functions that are needed. It's one example of how to open up that box and rearrange everything to start to shrink it down, start to get that future capability where we want it to be from where it will be on the first lunar landings.
Yeah, Ryan, I think Greg kind of hit on the human performance part to this, right? So we're talking about suit technology development and improvements, right? We're going to have to go solve some of the mass problems, some of the radiation challenges, things of that nature. But there's a human part to this, right? So the cognitive loading, can you speak to that and the automation of systems and the confidence maybe that you have in your systems?
Yeah, absolutely. So right now my cognitive load is through the roof. So I get it. It's like you do want to offload those tasks and things that are going to happen. So there's no reason you should be thinking about them. But I worked with previously working with my students with heads-up display and augmented reality and those type of technologies have huge potential for helping with task assistance or even driving the tasks and helping with the safety environment. So I think those are cool technologies that'll kind of play into this as well. Just on a performance side, yes, there will be more EVAs in terms of futures of missions, but we also have to prevent the crew from burning out. So we need to figure out what's the right cadence for them. And for missions that are, I guess you can say 10 days or longer, like the 2 weeks kind of minimum on the surface somewhere would be that we're really looking at, I think it's like 24 hours within 7 days. So maybe 3 8-hour EVAs every other day kind of thing. And as you shorten the timeline, then you can cram more EVAs into that because if the crew burns out after 4 days, they're coming home anyway. So all that side of the performance then leads to the design of the suit and how long it lasts as well. I think that hits on some of the question. There's a lot in that question. So
yeah, there is. And maybe I'm going to bounce back to Greg. Greg hit on maybe some of the enhancements of driving at more time out the door, right? And so there was a question in the chat about decompression sickness and talking about cramming in more additional EVAs and how do we manage all the logistics associated with waste management and system recharge and the logistics associated. And so, Greg, do you want to maybe hit on that? So from a cognitive load part, we've kind of talked about, but also from just a physical limitation. And as we increase the cadence of EVAs, how does that maybe play out in the suit system, which includes the human, in the loop, right?
Sure. Talking about decompression for starters, by designing the suit to be able to operate nominally at 8.2 psia, that decreases the pre-breathe time, the time that it takes to get the nitrogen out of the blood. You can also potentially go and begin an EVA at 8.2 and then bring the pressure down to get enhanced mobility and less fatigue during the EVA. That plus automating the checkout sequence will take what is today on EMU an extremely long and fatiguing day for the crew members to perform an EVA and decrease it. It's still going to be a hard day. It's still 8 hours of work plus all the prep time and time afterwards that go into it, but it should make it more manageable for the crew. And for short missions, a week, perhaps go out every day. Having been done, excursions up on Devon Island myself on those long days, the sun never goes down, so why do you need to rest? We went out about every other day. We were there for close to 2 weeks, and I agree with Ryan that you just get fatigued. You need time to plan. You need time to reassess. So for those longer missions, every other day turnaround is probably as fast as we're going to see. The other part of the getting out the door longer, though, is also maintenance and servicing of the suit. There's a lot of time spent on the space station today, making sure that the suits are ready for EVA, treating the water loop, doing checkouts ahead of the EVA at the time, the day of EVA. Those can be designed to be reduced. We can design suits, and they're being designed now to have more tolerance to different types of water. So you probably don't need to do as much water scrubbing. And that's one example of where we can take that load off of maintaining the system. If anything goes wrong with the system, it needs to be easily serviced. You don't want to have to, we perform that service on the EMU today. We've replaced some parts that were never meant to be replaced on orbit, to the immense credit to everyone who's made that happen, from the crew all the way to the flight control and the engineers that figured out those processes. But this next suit, we can design it for those processes, for maintenance during the mission, so that that load is reduced as well.
Great info and great words. So we've got about 5 minutes left, and there's just so much to do with spacesuits, and specifically EVA and the challenges that we have to come. We've talked about a lot of those. There was a great panel on day one that talked about the partnership of humans and robots. I know some of the enhancements we talked about have to do with that data stream and maybe the interoperability and connectedness standards for how we interact with robots, potentially telerobotically by the crew on the surface. We could go down a whole bunch of rabbit holes. If I could bring it to one point, maybe ask this question. We talk about a lot of the challenges that we have, and we know a lot of those. There's probably some unknowns in there. But for all three of you, and I'll start with you, Ryan, is if you were to try and distill down in maybe a minute, what do you see as the biggest challenge that we get the biggest benefit of a lunar surface EVA operation to prove out that technology for Mars?
Yeah, awesome question. I'm gonna go with legs, because you could probably pick anything and talk about it forever. But we've been doing zero-G EVAs for decades, and just the capability of learning how to walk again with a new suit, new possible designs, multiple designs maybe. I think that the focus there is what's going to help us develop and figure out how we can trim mass or enhance our mobility and make it most efficient. So I think that the leg system is the next big thing to really open up the gates to exploring Mars.
All right. Natalie, what about you?
Yeah, I would definitely agree with that. I got to go on a geology excursion with some of our NASA geologists, and it was quite eye-opening. Climbing, getting down on your knees, chipping off things. So it was, you're not just staying in one area. You're not driving to one area and staying there. You're maybe driving to an area, getting out, looking at something, maybe climbing, kneeling, and then you're like, oh my gosh, well, if we're finding this here and that's kind of similar over there, what's that line, what's that boundary that we need to go look at and see how the formation is changing? And so we walk over to that area. And so there's a lot of definitely that lower mobility and upper torso mobility is going to teach us a lot for the Martian surface. And then other technologies like ingress, egress, and that pre-breathe protocol, understanding that mobility in that 8.2 PSID when you're in the suit, in vacuum or in the Martian atmosphere. That's going to go a long way. And then informatics, just really getting that to a more advanced place where we can be more autonomous. And so I think all of those are really key. And the dust, of course, while it's different dust, it's going to help us understand more what we need to do on the Martian surface to be able to then be in a more stringent requirement protocol for planetary protection. And so I think those are all very good.
All right, Greg, 30 seconds.
Yeah, I agree with all of those. They're all extremely important. In essence, gaining operational experience with the new suit system on the moon, it'll tell us about dust. It'll tell us how the mass works with the human for the particular mass that the suit system is. Planetary protection, how to do sampling without contaminating it with the human. They're all extremely important. And my takeaway is that we as a community have to get that suit, well, the crew member with that suit on the moon as soon as we can field it. I know that NASA is moving as quickly as possible to accomplish that mission objective. And that's going to tell us a whole lot. It's going to drive innovation and drive the community forward.
All right. Well, unfortunately, that brings us to the end of our time together today, and just tons of stuff to talk about. So I hope we'll have a follow-on panel at a future event. Ryan, at the end of your introduction, you used a phrase "spacesuit up," and I appreciate that phrase because I think it highlights the role we all play in space exploration, and specifically EVA. And as Natalie hit on, there is a public-facing website from the NASA EVA office that's nasa.gov/suitup, and I recommend for the audience and everyone that you could go there to find resources and information such as the EVA ConOps, publications of technology gaps, recent news from the EVA office. With all that, though, I want to give a huge thank you to our panelists for investing their time and participating on this panel. I want to thank you, the participants, for engaging in and advancing the conversation. And I want to thank Explore Mars for hosting the 2021 Humans to Mars Summit.